Hey everyone, I'm Yifan from Improbable. So I'm the tech lead of the internal platform team, which is a part of infrastructure at Improbable. And so today I'll be talking to you about OpenTracing on how we adopted the solution in the first place, how we went about actually choosing it, and how we're currently actually using it on the platform right now. And so to start, at Improbable, we build a product called SpatialOS, and SpatialOS is a distributed operating platform that enables people to actually build massive real-time online simulations and say that spread across thousands of machines. And so these simulations could be, like a game where you are playing with, hundreds of, tens of thousands of other players, or it could be, a city simulation where maybe you are just simulating the whole of London with all of the traffic and pedestrians and people all live and real in the world. And so if you are interested in finding more about SpatialOS, so we can talk about that afterwards. So to start with OpenTracing is, first of all, why tracing? As Richard I just talked about, with everyone's moving to microservices, and you're moving your system into a more independent, with a system with independent components. But then actually with a lot more components, it makes it incredibly harder to actually understand what's really going on within your system. And then understanding your server mesh, and then with introduction of more components, actually optimizing for user-facing latency is actually which one out of the 20 different microservices is when my request is hitting is actually causing this user issue, or seeing this 20-second request. And then just root causing analysis of backend errors where, I've got this backend error, but which user requests actually caused this to happen in the first place? And many other things that you might be interested to find out really how a request actually goes through your system. And then, so we're going to start looking into this. I think we landed on OpenTracing fairly quickly because, a large thing about OpenTracing is it's a vendor-neutral way. It's a vendor-neutral open standard for distributed tracing. And then, really, what that gives you is, you implement against one standard, and if you ever have to switch out between your different solutions, there's nothing you need to do, and you just switch out the reporter and tracer that's used. Your developer doesn't actually have to see any change. The API is stable. And then there's OpenTracing team has actually provided a diverse amount of language support that they have, and this includes Go, C++, Java, and most of the normal languages that you use, including Node and also Ruby as well, I believe. And then the other coolest thing is, because this tracing is not just simply done by putting another process in, that instruments what happens on your server. This you can write code to actually instrument as deep as you want within your code, and you can instrument as deep as you're willing to go for. Maybe this goes down to individual copying of bytes if you really wanted to do. And then. So we're talking about OpenTracing, and so there's actually OpenTracing is fairly simple. There's a very few core concepts I will be walking through in the next few slides, and these include from the top level trace, spans, and the span context. So to start with everything, what is a trace? So a trace tells you a story of a transaction or a workflow actually as it propagates through a system, and whether it's a Kubernetes system or whether it could be a very fairly complex single binary large process. And so in the diagram that you've seen, that I shamelessly stole from the OpenTracing website. So you can see a request come in from the client as the flow goes, and initially hits the load balancer, you go through all successful, you go through billing to make sure the request is tracked, return, and then you go to fetch the resource, and then that's returned to you. And I'm sure we've all drawn plenty of this system design diagrams during our design phase, but then really what does it mean? What does that request really look like when it's actually processing real user requests? And so a more interesting thing to look at might be, actually if we draw this out on a timeline, and you can see, for each client, they track for request start to end is once a client sends a response to a client sends a request and the client receiving the response. And then the part of it, see a bit of latency in the front, for hitting the load balancer. And once it hits the load balancer, there's a bit of intra-cluster latency for hitting the authorization server, and so on and so forth. So this is the kind of thing that would be great to see, about your system if you can actually just get that without actually having to draw out your architecture diagram every single time when you're reasoning about a public-facing API. And then we move on to a span. And so just like you've seen like from the previous diagram, so every one of those horizontal lines can be its individual span. And then a span has a few top-level metadata that's attached to it. This includes, operation name, start time, end time, and so some of the more interesting thing is so span tags and span logs. So span tags is just arbitrary metadata that you can attach to the spans that you create in code. And then, so going back to the previous slide, and say like for auth, you might be interested to say like, oh, what is the subject for my request? Or like, what is the main version of my binary that I've deployed? Or what is the peer address of the client that's actually requesting? And then, so span logs is very similar, but the special thing about like tracing span logs compared to normal logs is a trace is aimed to log the complete lifecycle of that request. And so like this can even include like low-level debug logs, and where you can like happily print log everything in there, because traces are sampled, so that you don't actually have to worry about actually you're logging too much, because then you can actually just tune down your sampling rate. But trace span logs ensures that you have a complete view of actually exactly what has happened inside of your request. And then the last but not least, so span context is a core concept actually that encompasses a lot of this, and this is a code concept that you access when you're writing code to instrument parts of your code when you create one of these spans. And so when you create one of these spans, and you can use that to add adding tags, adding logs to create child spans and create like follows off. And then so once you get familiar with spans, then at the beginning, it's not so interesting if you only have a single span that tracks the start to the end of request, which is actually what the monetary latency data gives us. And so with that, you start to try to create actually like children spans to say like that client request is the top level, the root span of the whole request, and then the load balancer span is the child of that, and then authorization is the child of that, but then billing is the follow off of the authorization, and the same for the resource allocation. So the span, like the parenting of spans, can be as deeply nested as you want it to be, and it gives you actually like very interesting like causality like within your services for you to be able to track, which one of the requests actually kicked off my next one, and for you to see how it actually propagated through your system. And then, so that's the, so OpenTracing, it was super simple. And so with OpenTracing, there's many like OpenTracing platforms that provides like OpenTracing API compliant like SDKs. So like this includes OpenZipkin. You probably have heard a lot of these names: OpenZipkin, Jaeger, AppDash, Lightstep. I could probably go on for a while, but then we chose none of that. And so we went for actual probably a lot of people haven't heard this. It's a Stackdriver Trace. This is provided by Google, and it's Google's customer-facing distributed tracing system. So the cool thing is the fact that actually with most other tracing solutions, there's actually a whole bunch of setup that's actually required to be able to deploy that whole ecosystem. Say with Jaeger, you need to deploy sidecars for every single one of the pods that you run to be able to actually send that thing to another collector that you need to orchestrate another way, and then set up the UI in a separate container. And then dealing with the deployment of those services can be fairly complex if you want a reliable system. And then, so Google's this one provides you with a single API endpoint, and you just get a service count, and then funnel all of your traces too for free. And they still claim it's free. When they start charging, I have no idea. But then I think we're just going to use it until it actually, starts becoming expensive. So now, this is the tracing in general. So how do we actually do it at Improbable? And so the thing with microservices at Improbable is that because we built this stack up from Go very fresh, from just over 2 years ago, so we actually, across all of our services, it's all implemented through Go. And then as a core responsibility of the internal platform team, we actually provide a base server library for all devs to use to actually implement their grpc and HTTP servers. And so because we actually control this base layer of like the base server, we're able to actually enforce a lot of things on the base layer without, and switching out things as needed without the individual developers have to worry about a thing. So they just register, oh, I register my HTTP handlers, here's how I register my grpc handlers, and that's it. Like tracing, logging, like metrics, monitoring, and all of like panic recovery and whatnot is all included by default for all of your handlers. And then the other one is now you've got things, taking care of things coming in without like going out. So we have the commonized dialers for all of the components within our system such that we can enforce, client-side middlewares as well. So I'll be talking about on the next slide. And so even for like DB accesses, we use things that's actually backed by protobufs to use to actually generate code for accessing databases. And so in terms of actually tracking the operations in DB and adding traces to those, we were able to actually just add those to generated code without actually people having to see them. And then goes to enforcing traces. Like with our stack, it was relatively simple. So on the base server that you saw on the previous slide, we enforce a bunch of standard like server-side and client-side middlewares. For grpc, it's the same thing, but it's called interceptors. And then with the DB accessors, we do the same. And then, so like with Stackdriver, all traces get reported to the same place. It was incredibly simple. And then, so because we were able to actually control those low-level things, we were able to add a whole bunch of standard tags in, which makes debugging super easy. And so the binary version, so you want to make sure what kind of different version of stack that it actually went through, because for different components of system, it's owned by different teams, it's released at different times. It's useful to reason about, look at the version, to go back to the code, oh, this was the version of the binary it actually hit. And then the request ID is something that we actually generate for a trace actually entering into the system. So for a request entering into the system such that actually this thing is also persists in all log lines. So you can easily look at a trace and go, oh, actually I wonder what are all of the relevant logs I have in Elasticsearch. Take that request ID, bash it into Kibana, and then see all of the relevant logs, as well as seeing our tracing data. And environment, or subject, and peer address, and a whole bunch of other things as well. And then now, so the other thing is, now you have tracing, if you start tracing a bunch of your requests, really, how can you use that to your advantage? So the biggest thing is, with tracing, what we're really trying to optimize for is to know exactly what our servers are doing at the time with processing the request. And so when you initially start adding tracing, it might be interesting for you to see, oh, there are certain random gaps within different parts of the traces that you have generated. And then really it's trying to identify what those gaps are, but then the UI showing you the gap is the idea for you to look in code to find out where it is and try to account for that missing time. And then, so the other one is, so with OpenTracing, given that you have the full control of the code, you can just add logical names to all of your reasonably sized operations. This could be, memcache accesses, DB accessing, or maybe it's just a logical operation that was so large that you just want to add in a name to give it another parent span to make the trace actually easier to read. And then, and then breaking down large spans into child spans. So with all of that, I'm going to show you some hopefully funny, maybe also interesting diagrams that we've seen after we start using tracing. And so this is one of the crazy queries that we found after we actually implemented this is actually one of our RPC servers on one of the gets was actually somehow ended up doing 20 of the same request. And to actually get the same data, it was only taking the first one that returned. And so we did not see this until we actually hit this. And then, so this one is another funny one for slow encoding. So the actual like server processing time only took very little time, and the other 150 seconds that you saw is actually just doing a JSON encoding, because the server was actually like so overloaded with the number of like requests it had at the same time that it actually took about 160 seconds to respond to this request. And then because like we had accounted for as much things in the middle as possible, and then so we were easily able to identify actually that missing gap was actually used just in the binary encoding. And then later, like a benchmark test showed that it was super simple. Yeah, it was definitely the case. And then, so the part I talked about creating large span, like new spans for large operations. So we had this, like all of the data store operations, like for actually using cloud data store. But then actually, like without this, it was incredibly hard to actually see what it was actually doing, because it was just actually a whole bunch of DB requests. And at the end, like for one of the libraries that we use, we added another layer of like logical operation to make sure one's created all the time, so that you can actually see that, oh, those queries belongs to that operation, not like other ones that exist. And obviously sometimes you just get crazy traces like these, where it actually simply goes through too many services, but actually having a trace like this still helps you easily identify exactly how the request is actually flowing through the system. And then, and this request was actually only like 10 seconds, but it was actually making many, many calls. So, and with all of that, you can see actually like OpenTracing is actually a super simple concept that can be actually adapted to many systems. And actually adding OpenTracing to your system and choosing your like OpenTracing implementation is actually super simple. So with especially if you actually control the base library for all of your dev teams, or actually maybe even think about like start providing that for all of your other like platform services dev teams, is a super simple way to actually have more of an opinion and have an easy way for like the infrastructure team to be able to have more of an opinion to enforce like better monitoring, better tracing, better logging, and everything, so that developer have an easy way of doing things just simply by default, without people having to worry about, oh, how do I log it and do those things? Because when you give people options, they make mistakes. So like with base server, this is kind of our most opinionated way of actually building this, or like the improbable way of doing production services.